The second integration method that we have to learn is integration by parts. Now, the integration by substitution was synonymous to our reverse chain rule. Integration by parts is going to be synonymous to our reverse product rule. So in order to define what integration by parts is going to look like, let's begin by defining two functions. So let u and v, they are two real functions, and we're going to consider the product u times v. One thing we know about the product of these two functions is that when we do the derivative of the product, the derivative of u times v with respect to x, we can use the product rule. So that's going to be the derivative of u with respect to x times the function v plus the function u times the derivative with respect to x of the function v. Now, what I want to do at this point is I would like to multiply this expression by dx. So if I do that, I get d of u times v with respect to x times dx. And I'm going to do that distributed in the right hand side. So du dx times dx times v plus u times dv dx times dx. And then I'm going to simplify all of these differentials of x, and I'm going to get du times v is equal to v times du plus u times dv. Now I want to integrate this to go back to the original product u times v, and I'm going to have the integral of du v is the integral of v du plus the integral of u dv. The integral of du times v is going to be equal to u times v, and then these two integrals remain the same, v du plus the integral of u dv. And so what we're going to have in general for integration by parts is that whenever we integrate a function u in a product with the differential of a different function v, that is going to be the same as taking the product of the two functions minus the integral of the product of v with the differential of u. This is the rule for integration by parts. Let's see how we can use this rule in an example. So we have find the integral of x cosine of x with respect to x. In this integral, we know clearly that since there's no composition in the way that it was needed for substitution, we cannot use that method here. So what we can do is to use the method of integration by parts. So how does it work? We are going to identify one of these two functions, x or cosine of x. We are going to give them a name. So one of them is going to be u and the other one is going to be dv. The key in assigning the role lies in the right hand side of the rule. So as you can see, the function u will appear in the right hand side as du. It's going to be differentiated. So it is convenient for me to choose in the role of u a function that is going to get simplified in terms of if it's a polynomial, for example, it will be reduced in 1 degree. So it is very useful to simplify the problem like that by choosing a function u that I know the derivative is going to be more convenient. In this case, the thing that is a little bit of difficult here to integrate is the fact that I'm multiplying the cosine by x. So if I were to call x u, so if I make u equals to x, then in the right hand side of the rule I'm going to have the derivative of x, which is 1. So that is going to simplify my problem quite a bit. So I'm going to define the two values. I'm going to define u as x, and I'm going to define dv as anything else that is not x. So cosine of x times dx. That's going to be dv. Now, in order to get du, I need to differentiate u. So I'm going to get du is equal to 1 dx. And if I want to get v, then what I have to do is integrate cosine of x, which we know is sine of x. So v is going to be sine of x. So using parts, the integral of x cosine of x dx is going to look like u times v comes first, so x sine of x minus the integral of v, which is sine of x, du, which is dx. After I've done the substitution, I can evaluate the integral of sine of x. So this is going to be x sine of x minus the integral of sine of x. That's going to be minus cosine of x. And everything plus the integrating constant c. So my integral is going to be x sine of x plus cosine of x plus c. And that would be the final answer. Let's do one more example. Find the integral of x ln x with respect to x. I'm going to define in this case the function u as ln x. And I'm going to say then that dv is going to be x dx. With this definition, we get that the u over the x is going to be 1 over x. So the u is going to be 1 over x dx. And the function v is going to be x squared divided by 2. Now I'm going to substitute in my integral. Integral of x ln x dx is going to be ln x times v, which is x squared over 2, minus the integral of v, x squared over 2, times du, which is 1 over x dx. So this is going to be 1/2 x squared ln x minus, and I can simplify x squared with x here, and I get 1/2 integral of x dx, and that is 1/2 x squared ln x minus 1/2 of the integral of x is x squared over 2 plus the integrating constant c. So the final answer, I can write it as 1/2 of x squared ln x minus 1 plus c. In the previous example, notice how I chose ln x to be u, because I knew that if I chose it as v, I would have to integrate it. And the problem was that I didn't know what the integral of ln x was. And the problem is that ln x doesn't have an integral that is familiar to us already. But with integration by parts, we can do this integral very easily. So what we're going to do is we're going to do a similar process to what we did before. And we're going to call u as ln x again this time. So we're going to say u is ln x. And you would think there's nothing else in that integral. What am I going to call as dv? Well, we're going to call dv as dx. So that when I do the differential for u, du is going to be 1 over x dx. And when I integrate dv, I get v is equal to x. Now with these two functions in mind, I will now calculate the integral of ln x with respect to x. And now it's going to be u times v. So it's going to be ln x times x minus the integral of v du. So that is x times 1 over x dx. Now we know that we can simplify x with x, and that integral is the integral of 1. So this is going to be x ln x minus the integral of dx, and the integral of the x is the same as x. So x ln x minus x plus the integration constant c. So the final answer is x ln x minus 1 plus the integration constant c. Now let's do one exam style question. Using integration by parts, find the integral of x squared cosine of x dx. Now we are going to say, in this case, we're going to define the function u as x squared. The reason is the same one that we gave for the first example that we did. The function x squared is not very comfortable for us in this integral. I know that it's going to be differentiated in the right hand side, so I prefer to lose 1 degree of this polynomial, so I'm going to call u as x squared. And so I'm going to call dv as cosine of x dx. Now the differential of u is going to be the derivative of x squared, so du is going to be 2x dx, and v is going to be the integral of cosine of x, so v is going to be sine of x. And we're going to substitute. So the integral of x squared cosine of x dx is going to be the product of u and v, so x squared times sine x minus the integral of v du, so sine of x times 2x dx. This is equal to x squared sine of x minus 2 integral of x sine of x dx. Now the problem was simplified when I did this substitution, but I still have an issue with this integral. I still don't know how to integrate this. So I'm going to use parts only on this integral one more time. So just for that last integral, I'm going to define u as x, and then the differential of u is going to be equal to the differential of x. And I'm going to define dv as sine x dx, and then the function v is going to be minus cosine of x. Now I'm going to do a substitution for that integral only. So everything else is going to remain the same, minus 2, and then this integral I'm going to do the integration by parts. So that is going to be minus cosine of x times x minus the integral of minus cosine of x times dx. So that becomes x squared sine x minus 2 minus x cosine of x plus the integral of cosine of x dx. So the final answer for the integral is x squared sine of x plus 2x cosine of x minus 2 sine of x, and then plus the integration constant